Hello. All right. So today we're going to talk about the law of sines and the law of cosines. All right. So to start off, let's do a little review of stuff that we've done previously. So this is the review. So previously, when we've done triangles, we've done right triangles. And a right triangle is basically a triangle that has, one of the angles is at 90 degrees, right? So kind of the classic right angle, right triangle, looks something like this. There's your 90-degree angle. You have sides A, B, and then you have a hypotenuse C. And let's say, you can define each of these angles in a particular way. So for right triangles, we know that you can use Pythagorean theorem, right? A squared plus B squared equals C squared, where C is the hypotenuse, right? Hypotenuse. And we also know hypotenuse is always the longest side. We also know that you can use trig, SOHCAHTOA, right? So sine theta, in this case, is opposite over adjacent. Opposite over hypotenuse, so that's B over C. Cosine theta is adjacent over hypotenuse, so that's A over C. And then tan theta is opposite over adjacent, which is B over A. Okay? We also know that all angles add up to 180 degrees. All right. So that's all the stuff that we've done before. But now what we're going to do is we're going to study non-right triangles. Okay? And so one of the things is when you have non-right triangles, it turns out some of the rules are different. So non-right triangles. All right, so non-right triangles, these are called oblique triangles. I don't know how important it is for you to actually know the terminology, but that's what they're called. So I'll draw you some examples of non-right triangles. So here's a non-right triangle. It's got three sides, but none of those angles in there are 90 degrees. So this one is wider than 90. How about something like this? Again, no right triangles. This is a big angle that's greater than 90. One that you might be familiar with, the equilateral triangle. So the equilateral triangle has 60-degree angles. Or also these kind of, tall, skinny isosceles triangles also. Okay, so when you have non-right triangles, you have these oblique triangles. Well, what works? Does Pythagorean theorem work? And the answer is no. So Pythagorean theorem is out. The SOHCAHTOA work? And the answer again, no. So those were our two main tools we had for non-right triangles. But those only work if one of the angles is 90 degrees, right? Because if you look at this, like C was the hypotenuse. Obviously, we don't have a hypotenuse here. We have, there's the longest side for some of these, but hypotenuse was specifically the angle opposite the 90 degrees angle. But one thing that is true here is that we have that all angles add up to 180 degrees. So that one is, in fact, good. Okay, and actually we're going to use that quite a bit. Obviously, also they're triangles that have three sides. So one of the ways of thinking about this is that we have a set of tools for right triangles, and we're going to have a different set of tools for oblique triangles. And specifically, the tools that we have for those are the law of sines and the law of cosines. Okay, so law of sines and law of cosines, those are our two main ways that we're going to try to do these kind of non-right triangles. So I'll tell you that in general, when you get onto this a little bit later, there are a lot of cases where you can turn an oblique triangle into a right triangle or two right triangles. For example, it's kind of a classic thing that it's very common to do is to take one of these oblique triangles and try to like split it in such a way that you get kind of two right triangles. So you have a right triangle on this side and a right triangle on this side. Or if you have this one where this angle is kind of going outside, you drop a line there. And again, you can kind of make two right triangles. You can see this one, and then you can see this big one is another right triangle. So that's kind of like a classic thing. If you really love right triangles, it turns out that you can turn these oblique triangles into right triangles and then use, SOHCAHTOA and Pythagorean theorem and stuff like that. But, sometimes it's nice to have just a specialized tool for a specialized job. And that's basically what the law of sines, the law of cosines are meant to do. So let's look at the law of sines first. Okay. So the law of sines. So we have a triangle. And we have sides A, B, and C. And what we're going to do is we're going to show angles as capital. So this angle here is capital A. This angle over here is capital C. And this one over here is capital B. And you can see that the way that this notation works is that the angle A is opposite the side little a. The angle B is opposite the side little b. The angle C is opposite the side little c. Okay, so the law of sines basically relates the angle and the side opposite it. So the law of sines is written like this. So it's sine A, sine of angle A over side A equals sine of angle B over side B, sine of angle C over side C. So that's the law of sines. Okay. Now, this is three parts, and basically when you're actually applying this, you would normally only like pick two. So you set these two equal, or you set these two equal, or you set these two equal, and so here, that's what I'm going to do. I'll do them in different colors. So when you're actually applying this, you kind of can mix and match what you want to equal what. So let's say you could do sine A over A is equal to sine B over B, or you can do sine A over A is equal to sine C over C, or you can do sine B over B equals sine C over C. All right, so you can kind of mix and match depending on what kind of problem you're doing. But basically, if you recognize the template, which is that it's sine of an angle and then the side opposite divided by the side opposite that angle, that's basically what it is. And it says that you can do that for any pair. All right. All right, so let's do an example where we apply the law of sines. So the law of sines works for any oblique triangle. So let's do this example. So we have a triangle. And what we have is this side is 10. This side is B, we don't know it. And this side C, we don't know it. And we know some angles. So we know that this angle A is 50 degrees. And we know that this angle C is 30 degrees. And this angle B is unknown. Okay? So if we look at this, let's circle the things that we know. So we know this side, we know this angle, and we know this angle. Okay, so this would be kind of a classic law of sines kind of triangle. So we have an angle and the side opposite. That's good. And then we have this angle, but we don't know that side opposite. So when we're doing this, we're going to apply the law of sines, but we're going to do sine A over A, sine C over C, and that C should be our only unknown. So it'll look something like this. So sine A over A equals sine C over C. And I basically chose that kind of strategically, where I would kind of pick this pair such that I know everything except one of the things. And if I have one unknown, then I should be able to solve for it. So this is sine of 50 degrees divided by A is 10. And then this is sine 30 degrees and then divided by C. All right, so you have to solve for C. So there are a couple of different ways you can approach this. Basically, you could cross multiply. If you feel comfortable cross multiplying, you can just cross multiply. That's the easiest thing. The longer way is you would do multiply both sides by C, multiply both sides by 10, divide both sides by 50. That's kind of a longer way. I'm going to show you kind of maybe a little bit of a shorter way. Is that's something in between those two methods, which is first to flip both sides. So if what you want is a denominator, what you should do is flip both sides. So if I flip both sides, I get 10 over sine 50 equals C over sine 30. And if I'm solving for C here, what I'm going to do is I'm going to multiply by sine 30 to both sides. And the point of that is just to kind of cancel that out. Okay? So if I do that, I get C. I get sine 30 times 10. Normally, the way this is written, usually you put the number in front of the sign. So that's what I'm going to do. That's just kind of a style thing. But it doesn't really change your calculation, but that's typically how you would see this written. Okay? So I get 10 sine 30 over sine 50. And you have your calculator. Listen, if this is like on the homework or something, if you just give me that, I'll accept it, but you can put it in your calculator. If you don't have a scientific calculator, let's say that you never had one, or you left it at school, or you lost it and on your way home or whatever, there are a lot of online calculators that will do this for you. I think even Google has a built-in calculator that you can kind of plug this into and get a number for. So I got, I'm going to round this to the nearest tenth. So I got 6.5. All right. So C equals 6.5. Okay. So I know this side. Here, I'll put this in green. So this is 6.5. All right. The next thing is to solve for B. So one thing I know is that all the angles have to add up to 180. So 50 degrees plus 30 degrees plus B has to be equal to 180 degrees. So I can solve for B just by subtracting 180 minus 50 minus 30. So right, and B is equal to 100 degrees. So using that rule that all the angles have to add up to that. Okay. So I know B. I know all the sides. I don't know this side, little b. So I'm going to have to apply the law of sines again. So let's use the law of sines again. So I'm going to do this sine A over A and sine B over B. And they're actually, since I know C, I could also have done sine C over C if I wanted to. At this point, near the end, you'll have some options on how you want to do this. So I'm going to get sine of 50 over 10 equals sine of 100 over B. And I'm going to flip both sides. So I flip both of these. So these are equal to each other. So when I flip them, they should all still be equal to each other. Okay, and then to solve for b, I'm going to multiply both sides by this denominator sine of 100. Okay, so this cancels out. And I get b equal to 10 times sine 100 divided by sine 50 degrees. And so I get b is equal to, I'll just plug this in my calculator once again, 10 times sine 100 divided by sine of 50. All right, I got 12 point, let's round that to 9, 12.9. Okay, and there we go. So using the law of sines, I was able to solve for all of these sides. All right, so that is how you apply the law of sines. All right, so I'm going to give you one to try out on your own. This is a different kind of looking triangle. I'm going to try to use a different black pen, which I think, so you try. All right. So I'm going to show you this. I think it's, hopefully you're taking notes. Again, taking notes is a good way of approaching these videos. There we go. So we have a side A, a side B, oh, I'm sorry, this is side C, and this is B is equal to 22. All right, and then we have this angle right here. A equals 98 degrees. And this angle in here, I'll kind of pull it out over here, is equal to 45 degrees. And this angle B is unknown. Okay, so here, let me write that a little bit better. So this angle right here is 98 degrees. All right, that's angle A, and this angle is capital C. All right, sorry, I probably should have drawn that a little bit bigger. Okay, so what we want to do is we want to apply the law of sines to this to solve for this side A, this side C, and this angle B. Okay, so why don't you try that? I'll give you a couple seconds to pause it to try to do it yourself. And then we'll go through it. And if you want, you can just see kind of the first equation and then kind of go from there, but I'll show you that. Okay. Here we go. So what I do first is they give us two angles here. I'm just going to solve for this angle B first, right? So I know that angle B should be 180 degrees minus these other two angles. Right? That's the same as saying all the angles should be equal, should add up to 180 degrees. Basically, like these two angles take up a certain amount, and then whatever's remaining has to be equal to B. All right, so I get 180 minus 98 minus 45. When I do that, I get, is this 45? Oh, I'm sorry, this angle is, in my notes I looked at it different. It's 43, I apologize. If you did that whole thing with 45, I'm sorry, I can't read my own handwriting. Your answers would probably be a little bit different. Okay. I'm not going to redo this video, but that is a mistake. I'm sorry for that. All right, so let's look at what we know, what's given to us. So now we know this angle, we know this side, and we know this angle. And now we know this angle is equal to 39. Okay. Yep, 39. So what we don't know is side A or side C. So this is where we're going to use the law of sines. So since we know angle B and the side B, we're going to use sine B over B. And then let's solve for a. So we're going to use this angle, which we know, sine a over a. So when we plug this in, sine of 39 degrees divided by 22 is equal to sine a, which is 98 degrees, divided by side a. And we want to solve for a, so I'm going to flip both of them. So I can get 22 over sine 39 degrees equals a over sine 98 degrees. So then I'm going to multiply both sides by sine 98 degrees. Cancels out there. So a is equal to, again, I always like to put the number in front of the sign. So it's 22 sine 98 degrees over sine 39 degrees. Yeah, you know, it's kind of weird. Like, technically putting the 22 in front of the sign is mainly just kind of a style thing. I don't even know where I picked it up, but it's one of these things where, you know, math culture has a certain kind of convention for how things should look, and it's just very common to see that sort of thing. Okay, so we have 22 times sine 98 degrees divided by sine 39 degrees, and what we get is we get 34.6. So side A is 34.6. Okay. All right, so now we need side C. So let's do the same thing. So here we'll just do sine B over B equals sine C over C. And we know sine B, sine of 39 degrees over 22, side B is 22, equals sine 43 degrees divided by C. So we flip both sides. 22 over sine 39 degrees equals C sine 43 degrees. And again, you know, this algebra stuff, there are a lot of ways of doing it. I'm just showing a way that I think will be less confusing. Honestly, the quickest way is to do cross multiplication if you feel comfortable with cross multiplication. But I sort of feel like I think I tried to explain that once as a shortcut because I was feeling lazy about it. But and I feel like a lot of people got confused by that. But if you understand that, you can, whatever algebraic way you like doing it, that's fine with me. I'll accept. I'm very flexible on what kind of things I will accept as correct. Basically, my rule of thumb is if I can't do it in my head, I'm going to assume that you can't do it in your head either. Maybe that's arrogant or whatever, but that's kind of my rule of thumb. All right, so when I do this, I get 23.8. So there we go. Our side is 23.8. So if you started doing this with a different angle, your answers might be slightly different, but if your equations basically look the same, then you're okay. I'm sorry about that. All right. Okay, so I want to take a second to do something that I'm not going to test you on, but I think it's, especially if you take more math courses, it's going to be important that you understand how to do these sort of things. But it's deriving, we're going to derive the law of sines. Okay? So again, the thing about derivations is that I think understanding how to do a derivation, even memorizing a derivation, is actually kind of nice. And the reason is because it allows you to have a better understanding of where the equation comes from. It allows you to connect, this topic to other topics we've done. So we're actually going to use some right triangle trigonometry. And also you'll have an idea of when this equation is applicable and when it's not applicable. And so in general, derivations are very good for you to do. If this is like the last math course you're ever going to take, maybe it doesn't matter. But definitely, if you're thinking of moving on, having an understanding of these derivations, even memorizing them, is not a bad idea. All right, so I'm just going to show, I have an oblique triangle with angle A and B, sides B and side A. There's also angle C and side C, but I'm not going to draw that because you'll see in a second. So the derivation for the law of sines is basically you take this, and what we're going to do is we're going to turn this oblique angle into two right triangles by dropping a line right here. We have two right triangles, okay? So we have our first right triangle, and I'm going to call this side H. So we have one right triangle, which is the left triangle, looks like this. So it has B, A, H, okay? And then we have another right triangle, I'll do it in green, which is this one. Angle B, A, and side H. Okay? All right, and that's also a right triangle. Because it's a right triangle, we can use trigonometry. So here I have sine, I have A, the angle, the opposite side, and the hypotenuse. So that leads me to think that I can use sine. So sine of A is equal to opposite H over hypotenuse B. And over here, well, here I'll solve for H. So H, if I multiply both sides by B, H is equal to B sine A. Right? So that's stuff that we've done before. Here I'll do the same thing here. So again, I have the opposite and the hypotenuse, so I'm going to do sine again. So sine B is equal to H over A. If I solve for H by multiplying both sides by A, I get H is equal to A sine B. And so what I have here is I have an equation for H and another equation for H. So that means that this and this should be equal. Okay? So those two are equal to each other. And so if I write that B sine A is equal to A sine B, I just divide both sides by A, and then I divide both sides by B, so I can actually do both simultaneously if I divide both sides by AB. So the B's cancel here. And I get sine A over A is equal to sine B over B. Right? So that's one part of the law of sines. So I think that's nice because it connects some of our right triangle trigonometry to and some algebra to determine this. So what you might notice, it doesn't have sine C over C, and the reason is because you'd have to just break up the triangle in a different way. So let's say we had our triangle like this, and let's say that we had sine A, angle A, side A, and this time we have angle C and side C. And so the way you would do this is you would try to drop another right triangle here, but in order to get kind of a right angle, what you'd have to do is you'd have to drop it on the outside, so it'd be something like this. Okay, and this would be our side H over here. So basically what you would get is you would do the same exact thing, except you would have a kind of a triangle that looked like this, where this is H, this is side A, and then you'd have this outer angle C, and then you would have this other triangle. The other right triangle would be kind of this big one, so it goes all the way from edge to edge like this, and this side would be H, this angle would be A, and then this hypotenuse would be C. Okay, so it turns out if you do the same thing, when you do sine of this big angle C, that's also equal to the sine of this little angle in here. And so you basically get sine A over A equals sine C over C. So I'm not going to go through all of that, but it's basically the same progress. You just kind of cut it in a different, you just create your right triangle in a slightly different way to get the other third relationship. All right. So again, I think that's good to know. I think you would be a much stronger math student if you knew how to do that derivation. Okay. So the next thing I want to talk about is when doesn't the law of sines, I'm just going to do LOS, law of sines, when doesn't the law of sines work? Okay, so it turns out the law of sines does not always work for every oblique triangle, depending on what information you're given. So I'll give you the situations when it works. So it works. I'll do this in green. In these situations, so if they give you an angle and a side and an angle, so the side is in between those two angles, law of sines will work. All right. If they give you an angle and the side where that side is not between the two angles, so they give you something like this, an angle, and then this side, law of sines works there as well. All right. So let me show you when it doesn't work. Doesn't work. Okay, when it doesn't work is if they give you a bunch of sides. So let's say they gave you 3 sides of the triangle, but they didn't give you any angles. Law of sines requires an angle, so you can't do that. It requires 2 angles, so you can't do that. So let's say it's side, angle, side. So they give you a side, 2 sides, and the angle in between them. This also does not work in the law of sines. Remember, and the reason it doesn't work is because here you need the side opposite the angle to apply the law of sines here. And you don't have a pair where you know both the angle and the side opposite. So we know this side, but we know this angle. We have this side, we have this angle. Law of sines doesn't work. So we're going to come back to this, but it turns out that there is a method that does work for these. And what does work for these is law of cosines. All right, so there's a reason we have this other law called the law of cosines, is because basically it helps you do these ones where the law of sines doesn't work. Now there is one kind of weird case where it sometimes works. So I'll use blue. So it sometimes, well, it works, but it's more complicated. I guess it's like sometimes they call it the ambiguous case. Okay? And that case is where they give you a side, and an angle. Okay. So here is why that case can happen. So you have something like this. You have a side. Here, I'll draw it like this. So you have a side, an angle, and then you have a side. So again, actually, the law of sines, you can apply this, but one of the issues you run into is that often when you apply this, if you're just given 2 sides, it's possible that the triangle could look like this, but for the same side lengths, it could also look something like this. Where basically this, all right, I didn't draw it that well, but this other side here could kind of flip out over there and still form kind of a triangle. So I'll give you an example that's drawn a little bit better. So let's say that we have a so let's say this is 10, Let's say this is 30 degrees, and let's say this is 7. Okay. Then it's possible that you can also draw another triangle with the same side. So this is 10. This is 30 degrees. And then you could have something that looks something like this, where that's 7. All right. So both of those triangles are consistent with those side lengths and that angle. So when you apply the law of sines, sometimes it's not entirely clear which triangle you're solving for. So specifically, let's say that we were solving for this angle right here. Let's call this B. So in this angle right here, B is greater than 90 degrees. It's greater than the right angle. Whereas here, B is less than 90 degrees. All right. So I'll show you kind of how that works. So let's do this, and I'll show you the kind of ambiguity. So we have, I'm going to do sine B over B. So I'm going to do sine B divided by 10 is equal to sine of 30 degrees, this angle, divided by 7. So if I solve for sine B by multiplying both sides by 10, I get sine B is equal to 10 sine 30 degrees divided by 7. So sine 30 is a half, so this turns out to be 5/7. So I have sine B equals 5/7. All right, so if we have sine of an angle equal to some number, do you remember how we solve that? Give you a second here to see if you remember. But the method we have is you apply the inverse operation to both sides. So the inverse operation is sine inverse and sine inverse. So we take both sides and we put them inside the sine inverse function. And so this is sine B. This is 5/7. And what happens is sine inverse of sine basically just gives you B here. So B is equal to sine inverse of 5/7. Okay, so let's plug in, sine inverse of 5/7. All right, so here we go. So sine inverse of 5 divided by 7 is 45.6 degrees. Okay? All right, so when we look at this, 45.6 degrees. If I were looking at this triangle, I'd go, 45.6 degrees seems to be less than 90 degrees, but when I look at this triangle, clearly this has to be greater than 90 degrees. So how could that be right? And the answer is that it's not right for this triangle. Basically, when you did this law of sines doesn't know how to distinguish between these two triangles, and it solved for this one. So this triangle is 45.6. So when I'm looking at this, if I know that if I'm, let's say, using this one, and I know it should be greater than 90, then I know that can't be the right answer. So if I'm looking for this triangle, so here in this one, B would be 45.6 degrees. But for this one, what I have to do is I have to take 180 degrees minus 45.6. And when I do that, I get 134.4. All right, so you have to be a little bit aware about which of these, in this particular where you give you side-side angle, whether your angle should be greater or less than 90. And that'll be kind of something that's kind of a little trick that you have to watch out for. I'm just going to do a little sidebar here about why that occurs. And one of the reasons that occurs is because the sine inverse, in order for the sine inverse to be a function, is over a restricted range from negative 90 degrees to 90 degrees. So when your calculator does this, it'll give you an answer between negative 90 and positive 90. All right. But there's another solution that usually is farther away. So for the sine function, if you remember, the sine function looks something like this, right? Where this is, usually I write it pi over 2, but this is 90 degrees and this is 180 degrees. So the maximum value of the sine function is 1. But let's say that we want a value over here. This is like 5/7. All right. So when you see this, when does this? It has a value right here, and it also has a value right here, right? So if you project across and then down, so this value is what we solve for. 45. I'm just going to round to 45, and this one should be 135. Okay. So that's basically what happens is usually it's restricted. It'll give you that first one, that first angle, but it won't give you the second one. But one of the reasons this is symmetric is, one of the reasons we can do this 180 minus this angle is because it's symmetric about this 90-degree part, at least for this little portion right. Well, actually the whole function is symmetric about that point. So it's 45 from there to there. So then you start from 180, and if you go 45 in, it should be the same corresponding point. All right. Here's another way of looking at it. If you want to look at it in terms of, triangles on the coordinate. So we have some angle theta over here. And so remember that when you draw these right triangles, the y component is equal to sine theta. Right? So if we want y is equal to 5/7, there's another angle in which that will also be 5/7, and that's when it's over here. So the angle from there to there will also create a triangle where y is equal to 5/7. And again, that's basically when you do sine inverse, it'll give you this small angle, but won't give you this big angle. If you want this bigger angle, you have to take 180 minus this. And again, because it's symmetric, this angle should be equal to that little angle. So 180 minus this little angle will give you this bigger angle. Okay, so that's something that you have to watch out for a little bit. So we'll do an example of one of those and how we take care of that. All right, so let's look at one of these ambiguous cases. So we have a triangle that looks like this. We have B equals 8. We have A equals 6. Side C, we have capital A is equal to 35 degrees. We have B, and we have C. So what do we know? We know this side, we know this side, and we have this angle. All right, so we have side-side angle, all right, where the angle is not between the two sides. So we're going to use the law of sines again. So when I look at this, we have A and the opposite. So that'll be basically one side. We have this side, but we don't know this angle, so this is going to be our other one that we use for law of sines. So it'd be sine of A over A equals sine B over B. And plug in sine of 35 degrees is A. Little a is 6. Sine of angle B, which we don't know, divided by side B, which is 8. And so I multiply both sides by 8. So I get sine B is equal to 8 sine 35 degrees divided by 6. I'm going to take the sine inverse of both sides. So the left-hand side goes in here, and the right-hand side goes in here. Okay, so here these cancel out. The sine inverse and sine just gives me whatever's inside, so that's B. And this is sine inverse of 8 sine 35 degrees divided by 6. So I'm going to plug this into my calculator and see what it gives me. So sine inverse of 8 times sine 35 divided by 6. All right, and it gives me 49.9 degrees. Okay, so this is where I'm going to circle this, but this is where I have to use that idea that have an idea of what I'm looking for. So I'm looking for this angle B, and one of the things I know about this angle B here is that this angle B has to be greater than 90 degrees. So it gave me an angle that's way less than 90 degrees, so that's a clear indication that this is that restricted range of the sine function. It's giving me the smallest angle, not necessarily the correct angle. So for this triangle, I know that B should be bigger than 90. So what I'm going to do is I'm going to take B, the actual value of B, I'm going to take 180 degrees, which is just, all the way around, minus the angle it gives me. So B is actually equal to 130.1. All right, so that's the only case where you have to be a little bit careful about that. It just kind of know whether you expect it to be bigger or less than 90 degrees. All right, so I know that this angle right here. Okay, then once I have that angle, then I can figure out angle C. So angle C is, I know that these angles have to add up to 180, so C is going to be 180 minus 35 degrees minus 130.1. So C is equal to 180 minus 35 minus 130.1, and I get 46.9 degrees. Okay, so I figured out this side right here. Oh no, this angle right here. 46.9 degrees. All right, now I have all the angles. I've got two of the sides. Now I just need to do law of sines one more time to solve for this. So I'm going to do sine of angle C over C, and I'm going to do sine of A over A. I could also do sine of B over B because I know that combination as well. So for solving side C, I'm going to flip both sides. Actually, let me just plug in first. Sine of 46.9 divided by C equals sine of 35 degrees over 6. So I'll flip both sides. C over 6 over. So all I did is I just flipped both sides. And then I'm going to multiply both sides by sine 46.9. Okay, so I get C is equal to 6 sine 46.9 degrees divided by sine of 35 degrees. All right, so plug that in, and that should wrap up this problem. One thing I'm thinking about here is sometimes people plug this in their calculator and they don't get the right answer. One of the things to check to make sure that you're doing is to make sure you're in degree mode if you're plugging in angles in degrees rather than radian mode. Radian mode will give you something else. 7.6 is our side length. Okay. All right, so that is the law of sines. So that should be okay for the first 5 homework assignments. All right, so we talked about before, but law of sines doesn't work for all of them. So specifically, law of sines doesn't work if you're given the 3 sides of a triangle, no angles, law of sines won't work. Or if you're given a side, angle, side, where the angle is between the 2 sides, law of sines also doesn't work there. So to get those possibilities, we have the law of cosines. All right. So it's kind of complementary. What the law of sines can't get, the law of cosines kind of cleans up. So I'll give you the law of cosines. It's a little bit more complicated. But again, we have our oblique triangle. We have sides A, B, and C. And we have angles capital A, capital C, and capital B. Where obviously angle A is opposite side A, angle B is opposite side B, angle C is opposite side C. Okay, so I will show you here. It's longer. It's A squared equals B squared plus C squared. And you might be thinking at this point, oh, that's a Pythagorean theorem. Well, it's a Pythagorean theorem with some extra stuff. So it's minus 2BC cosine of A. Okay, so that is the law of cosines. It's more complicated. Oblique triangles in general are more complicated than right triangles. But one of the things to mention here is that here, basically this side that side A is opposite angle A. So if you have this side, it should correspond to its opposite angle, A and A, all right? And then this stuff in between, these are just the other sides. All right. So you kind of, these two, one end and the other end has to match up, but basically just kind of fill in with the other sides. It doesn't matter if you do C squared first or B squared second, or if you do C and then B. They're multiplied here and they're added there, so the order doesn't really matter. Okay. So that's the basic structure, but I did it for this one side A, but you could also do it for the other sides as well. And if you do it for the other sides, it follows a similar sort of pattern. So B squared equals A squared plus C squared minus 2AC cosine. It's got to be the angle opposite this, which is angle B. Okay? Or you could solve for C. C squared equals A squared plus B squared minus 2AB cosine. The angle opposite the side C is capital C. All right. All right, so that's the law of cosines. I'm going to show you one of these. So let's say that we have a triangle that looks like this. So we have A is equal to 25, B is equal to 20, and we have C is equal to 18. So this is one of the ones that you could not do with the law of sines. Okay, which is you're given side, side, side. All right, but you have to solve for the angles. So what I'm going to do first is I'm going to solve for angle A. So I'm going to start off with A squared equals B squared plus C squared minus 2BC cosine angle A. All right, so I'm solving for angle A. So actually, if I look at this, that's the only thing that I don't know in here. So let's plug in some numbers. So 25 squared equals 20 squared plus 18 squared minus 2 times 20 times 18. Oh, yeah, no, I'm okay. For some reason, I made a mistake. Cosine of A. So the first thing you have to do is you have to solve for cosine of A. So what I'm going to do is I'm going to subtract this 20 squared from both sides. I'm also going to subtract this 18 squared from both sides. So I'm going to get 25 squared minus 20 squared minus 18 squared. And then equals 2 times 20 times 18. So at this point, just to kind of clean things up a little bit, I'm going to do a calculation here because I feel like having extra terms might be confusing for some people. So 25 squared minus 20 squared minus 18 squared is negative 99. Don't let that negative sign scare you because we're going to have a negative sign over here. but even if we didn't, it's still okay. So I'm going to have negative 2 times 20 times 18. Get negative 720. Cosine A. Here, let me just write this. Okay. So I'm going to divide both sides by negative 720. I'm having real problems writing the number 720. So it cancels out over here. So I'm going to put the cosine A on this side. Cosine A is negative 99 over negative 720. You take the inverse cosine of both sides. And we get cosine A is equal to negative 99 over negative 720. This is just A. And when you do this calculation, cosine inverse of negative 99 over negative 720, you could cancel out those negative signs too. That would be something you could do here. 82.1 degrees. Okay. Then what we have is, so we have this angle right here. I'll use red. So what we need is to solve one of these other angles. So let's do B. So if I do B, I do B squared equals A squared plus C squared minus 2AC cosine of B. So if I plug in those numbers for these, you know, I'm not going to claim that this is not tedious. It is what it is. You know, sometimes you might have to see this. If you take physics, I know I say this a lot, but if you take physics, you'll see this. Maybe not introductory physics, but it does come up in the physics curriculum. So I'm going to subtract the 25 squared, subtract the 18 squared, and then I'm going to divide by this. So cosine B. All right. So here, this is where, yeah, when it gets tedious, this is where you see me start not showing every step. But it's the same thing as before. So I'm going to take 20 squared minus 25 squared minus 18 squared. And then I'm going to divide that by negative 2 times 25 times 18. All right, yeah, so one of the problems of not being in a classroom is that there's no one to give me confused looks to tell me that I shouldn't be skipping steps. So here we are. And for this, I get B is equal to 52.4 degrees. All right. But it really was the same process as the other one. And then for the last angle, C, we know we have two of the angles, so the three angles should add up to 180 degrees. So 180 degrees minus 82.1 degrees minus 52.4 degrees. And what that gives you is 180 minus 82.1 minus 52.4. You get 45.5 degrees. Okay, so that would be how you use the law of cosines. Law of cosines, it can be a little bit messy, but it can come in handy sometimes. You know, there's some situations you have an oblique triangle. You have all the sides but none of the angles. You want to know the angles? Law of cosines is the correct tool for you. All right, so you should be able at this point to do all of the homework. There is one last thing I want to give you, which again is not required for you to be able to do the homework or even apply the law of cosines. But I want to do a little derivation. And I think, again, if you are kind of thinking of yourself as getting more serious about math, you should know how to do these derivations. It's kind of a good challenge. This would be something that you'll be expected to do more in the future. So let's say that we have axes and we have some point here, xy. And that point is part of a triangle. All right, that line isn't exactly straight, but you hopefully get the idea. Part of an oblique triangle that looks like this. Okay, so we have sides B, we have side A, and then we have side C, and we have this angle capital A. Okay, all right. So we're going to derive the law of sines. So what we're going to do first is we're going to turn it into a right triangle. So hopefully you kind of got that idea from before. So if I drop a line down here, I'm going to have a right triangle. So by dropping that down, I've created two different right triangles. So I'm going to draw them separately as two different angles. So we have this outer triangle. I'm going to call this, so this side is length y, by the way. Because that's just the xy coordinate, so this has to go y up. All right, so this bigger triangle looks like this. All right, and it has angle A, side y, and hypotenuse B. All right, and this side here is, again, it's a coordinate, so this is side x, because that from here to here, that's how far to the right you have to go to get to this point. So x to the right, y up, x to the right, y up. All right. Now there's a smaller triangle, which is this little one in here. So I'm going to draw that in green. It's going to look something like this. Okay. And for this triangle, you know that's the right angle. Here we have y, so because they share a side, this is y. This hypotenuse in this case is A. And then this is a little bit tricky, but this little piece right here, it's not x is from there to there and c is from there to there. So this little piece right here has to be, if you subtracted those two, let's say it was 10 and this was 7, so this would be 3. So this would be x minus c for whatever those are. Okay? Okay, so let's look at what we can get from this first triangle. So for this first triangle, I can use Pythagorean theorem because this is a right triangle, so I can use Pythagorean theorem and SOHCAHTOA. So I'm going to do x squared plus y squared is equal to b. So that's going to be something that we use a little bit later on. All right. Then I also know that I can do sine and cosine. So sine of A is equal to opposite y over hypotenuse b. And if I rearrange that to solve for y, y is equal to b sine A. And then I have cosine of A is equal to adjacent x over b hypotenuse. If I solve that for x, I get b cosine A. So I'm going to use those a little bit later. And then for my green triangle, I can also use Pythagorean theorem, right? So Pythagorean theorem says that a squared, here I'm going to do it over here, a squared equals the sum of the squares, so y squared plus this other side squared, which is x minus c squared. So here, at this point, I have to use FOIL. Yeah, so at this point, this is a really great derivation to know because it connects turning oblique triangles into a right triangle, finding the sides. This x minus c thing is good to know. Using Pythagorean theorem, using sine and cosine, and now it has FOIL. This is a great derivation to know to reinforce all that stuff that you know. So FOIL here would be x squared minus 2xc plus c squared. Now, this is where we're going to kind of simplify some stuff. So what we're going to do is right here, x squared plus y squared, if I connect this and this, that x squared plus y squared should just be equal to b. Oh, I'm sorry, this is b squared. So I get a squared equals, and this whole thing, x squared plus y squared, can be replaced with b squared. And then I have The other thing is that for this x, I have an equation for x, which is this. So I'm going to take this and I'm going to plug it in to there. And get minus 2b cosine A times c plus c squared. And at this point, it may look a little bit weird, but basically we've derived the law of cosines. We just have to rearrange it. So I'm going to put a squared, b squared, and then the c squared, I'm just going to move this forward because you can switch the order of addition. And then now we have minus 2. And again, you can switch the order of multiplication as well, right? So I'm going to move this c to be between the b and the cosine. So I get b, c, cosine A. There we go. The law of cosines. Okay? So that's a good one to know. I feel like you'll get some mileage out of kind of knowing that, practicing it, memorizing it. These skills are used lots of other places. So there we go. Law of sines, law of cosines, how you deal with oblique triangles. So you should be able to do the homework. Also, there is going to be a quiz, which is basically just additional homework questions, and that's going to have some law of sines, law of cosines. It's also going to have stuff that we did in the last lecture. So that was like 2 equations and 2 unknowns. And you should be able to do that. All right. If you have any questions, just email me. Let me know. I'll try to help you out any way I can. I hope you're doing well and that you're safe and healthy and that your families are safe and healthy. I'll talk to you next time.